Hello and welcome back. So we have understood, a matrix and its eigenvalues and eigenvectors, and then eigenvalue, eigenvector matrices, and then we understood that a matrix A can be decomposed into V lambda V inverse, an eigenvalue decomposition we can do. We understood that, but how exactly the eigenvalues and eigenvectors of a matrix should be found or can be found, we don't know, right? So let us try to understand how to find a matrix's eigenvalue eigenvectors in mathematics. You may not have to do this in machine learning, but understanding is better, right? So for to have a better understanding of the math, we just created this. Okay, so I've taken the matrix A 5 1 3 3, and we know that Ax is equal to lambda x, right? The x is the eigenvector matrix, eigenvector, and lambda is the eigenvalue. So if you have to find the eigenvectors and eigenvalues, first we need to find eigenvalues, and then using the eigenvalues we will find the eigenvectors. Okay, so first we need to find the lambda values. For this 2 by 2 matrix, there can be maximum 2 eigenvalues. So we need to find, if they're existing, right, we need to find 2 eigenvalues. Once we have those, right, we can find the eigenvectors also. So here I've taken the equation like Ax is equal to lambda x. If I take this lambda x onto the left side, it becomes equal to 0. I can multiply lambda with or x with identity matrix I. Okay, and then if I take x as common, it becomes a minus lambda I into x is equal to 0. Here in this equation, a minus lambda I cannot be invertible, right? That's the statement. A minus lambda I cannot be invertible. When I said it is not invertible, right? If it is invertible, what happens? Let us see. If it is invertible, that means there must be a matrix existing, right? A minus lambda I whole inverse must be existing. If that is there, if you multiply this equation with A minus lambda I inverse on both sides, what happens? On the right side it is anyway 0, so it's going to become 0. On the left side, A minus lambda I into A minus lambda I inverse, it becomes I. This whole thing becomes I into x becomes x is equal to 0. That is meaningless, right? You are trying to find an eigenvector which is 0 vector. It's meaningless, right? So definitely the A minus lambda I must be non-invertible matrix. So if it is non-invertible, when a matrix is non-invertible or singular, what that means? The determinant is 0. Using this concept, right, we'll find the eigenvalues. When I say determinant is 0, AD minus BC is 0. On an inverse matrix, 1 by AD minus BC. AD minus BC is the determinant, right? So A minus lambda I, what is A? 5 1 3 3, and lambda and I is 1 0 0 1. A two-dimensional matrix, an identity matrix is 1 0 0 1. When you subtract, you get this 5 minus lambda 1 3 3 minus lambda. So AD minus BC means this multiplied by this minus this multiplied by this. So 5 minus lambda into 3 minus lambda minus 3 into 1, which is an equation, lambda square minus 2 lambda plus 12, right? This is this is equal to 0. The determinant is equal to 0. That means determinant of this A minus lambda is 0. That means lambda square minus 8 lambda plus 12 is equal to 0. Using this equation we can find the lambda values, the eigen values we can find, right? You can actually make this equation as 2 lambda minus 2 into lambda minus 6. Either you substitute 6 or 2 in this equation, it becomes 0. That means lambda is equal to 2 and lambda 2 is equal to 6. Lambda 1 is equal to 2 and lambda 2 is equal to 6. That means now the eigenvalues for this matrix are 2 and 6. Using these values, we will find eigenvectors. Let us see how will we find it. So we know that A minus lambda I into x1 is equal to 0, right? That equation we found, right? Because A into x is equal to lambda x. You brought the lambda x onto the left hand side, it became A minus lambda x is equal to 0, and you kept I there and took x common, right? So A minus lambda 1 I into x is equal to 0. A minus lambda 2 I into x2 is equal to 0. right? If you substitute lambda 1 is equal to 6 and lambda 2 is equal to 2, you can find x1 and x2, the eigenvectors. So I substituted a value minus lambda 1 into I value and then into x, right? x1 I took it as x11. The superscript brackets is the row, right? First row and second row for the same column x1. First row and second column, second row for the same column 2, right? x2, right? So we multiplied, and when you solve this equation, right, I have got x1, you know, the 1 1 as the eigenvector. If you see this, x11 is equal to x12. If you take this as 1, right, that becomes 1. Okay. On this side, for the x2 eigenvector, when you multiply this, you got x22 is equal to minus x21. That means if you take x2 is equal to 1, x21 is equal to 1, it becomes minus 3. So this is 1 and this is minus 3. So 1 minus 3. This is how we'll derive the eigenvalues and eigenvectors for a matrix. So this is how we do eigenvalue decomposition. Once after getting eigenvectors and eigenvalues, you can combine eigenvectors into, you know, like this, right? Eigenvectors into one matrix like this, and eigenvalues into a diagonal matrix. That is eigenvalue decomposition. When you multiply this V and lambda and V inverse, you will get A. So that means A is decomposed into V and lambda, two matrices, where V, the eigenvectors matrix, contains the essence of the matrix, and eigenvalues explain you how much essence each vector extracted. So eigenvalues and eigenvectors are in pairs. The lambda 1 and the first eigenvector are pair. Lambda 2 and the second eigenvector are pairs. So if you say lambda 1 and eigenvector 1 are pairs, you are saying that the eigenvector 1 extracted 6 quantity, eigenvector 2 extracted 2 quantity, quantifying. The eigenvalues are quantifying and eigenvectors are extracting the essence. We need to remember this. In principal component analysis, this is the major point. In coming session, we will understand singular value decomposition, which is used extensively in many areas like the recommender systems, word vector creation, and the semantic analysis, right? The semantic analysis and word vector creation, and then another concept in NLP it is used. Okay, thank you.